discussing about the dual cycle to be led by me, Cadet Revilla, and my fellow members, Cadet Islera, Rios, Makadildig, Monton, and Cadet Claro.
Dual combustion engine, also known as a mixed cycle or limited pressure cycle. A dual combustion engine is a type of internal combustion engine that combines elements of both Otto and diesel cycles. It operates a four-stroke cycle and characterized by two distinct phases of heat addition, one at constant volume and another at constant pressure. It is called dual because combustion takes place in two parts, first at constant pressure and second at constant volume. First phase, constant pressure, continued combustion at constant pressure, similar to the diesel engine. Second phase, constant volume, heat is added rapidly as an Otto cycle, assuming no volume change.
I am Engine Cadet Makadildig and this is my report. The dual combustion cycle. Dual combustion cycle, also known as the limited pressure cycle, mixed cycle, cylinder cycle, and the Sabat cycle. It's a thermodynamic cycle used in internal combustion engines. Essentially, it combines aspects of both Otto cycle used in gasoline engines and the diesel cycle used in diesel engines. This means it uses a combination of constant volume and constant pressure. Heat addition processes for more efficient combustion. The provided image includes diagrams illustrating the different stages of this cycle. And the main advantage of a dual combustion cycle is a higher efficiency compared to a simpler cycle like the Otto or diesel cycle. This is achieved by combining aspects of both the constant volume heat addition of the Otto cycle and the constant pressure heat addition of the diesel cycle. By utilizing both methods of the engine can extract more work from fuel, leading to better fuel economy. And that's all.
The history of dual cycle. Dual cycle is known as the mixed cycle is a type of thermodynamic cycle that combines features of both the Otto cycle and diesel cycle. It was first introduced by Gustav Tinkler. The name dual cycles from the facts that heat is added into two different ways during the cycle. So the constant volume, just like in the Otto cycle, while constant pressure is just like a diesel cycle. So that's how the discovery of Gustav Tinkler, according to this story.
Good day, sir. This is Engine Cadet Monton and this is my report for Thermodynamics Finals. Dual cycle. Dual cycle is a thermodynamic cycle that models internal combustion engines more realistically than the Otto or diesel cycles by incorporating both constant volume and constant pressure heat addition phases. In short, air compressed heat is added at constant volume, then constant pressure the mixture expand and heat is rejected at constant volume. This sequence is more representative of real-world engine process. Advantage and disadvantage of dual cycle. While the dual cycle offers improved efficiency and more complete combustion compared to the Otto cycle, it also introduces complexities. The two-stage heat addition process requires more sophisticated engine design and control system. Furthermore, the dual cycles sensitively to fuel quality and air-fuel ratio can be a drawback.
So I'll be discussing the dual cycle process. So let me show you how the process of dual cycle using the paper. Okay, I will be discussing to you about the dual cycle process. So first is the process of 1 to 2 where isentropic compression. 2 to x where x is the addition. Just to clear, x is the addition of volume and pressure. 2 to x is the constant volume heat addition happens. Then from x to 3 where constant pressure addition occurs. Then followed by 3 to 4 cycle isentropic expansion. From 4 to 1 where heat are rejected or called exhaust. So that is the full cycle of a dual cycle.
These are the characteristics of dual cycle. First is the four-stroke engine combustion. The dual cycle is typically implemented in a four-stroke internal combustion engine. These include intake, compression, power, and exhaust, making the cycle efficient and suitable for high-power applications. The second is modern evolution of diesel cycle. The dual cycle combines the best features of both Otto and diesel cycles. It is considered an improved and more efficient version of the traditional diesel cycle, designed to optimize both power and fuel economy. The third is split heat addition process. One of the defining characteristics of dual cycle is the division of the heat addition phases into two parts. The first occurs at constant volume while the second continues at constant pressure. This split allows the engine to extract more useful work from the same amount of fuel. And lastly, the increased thermal efficiency. By combining constant volume and constant pressure, the dual cycle achieves higher thermal efficiency than either Otto and diesel cycles alone. This makes it ideal for heavy-duty applications such as marine engine and power generation.
Here we'll be discussing the solving. With this formula, it will help you solve the Q in Q out of the problem of dual cycle. The isentropic expansion as well as the compression and their volume addition and pressure addition. In next slide, it will help you to understand how to solve a dual cycle. I want you to watch this clip to understand or help you to solve a problem about dual cycle.
Dual combustion cycles are in a way a combination of the Otto cycle and the diesel cycle. They can be referred to as mixed cycle, Trinkler cycle, Seiliger cycle, or Sabat cycle. We had already made a distinction between the spark ignition engines, Otto cycle, and the compression ignition engines in the previous two main lectures, so make sure you have watched and studied those two 10-minute lectures before watching this. Because there is no spark involved in the dual or mixed cycles, they are usually categorized as a more modern variation of a diesel engine. Fuel is injected into the combustion chamber much sooner in a dual cycle than in a regular diesel cycle. For this reason, since fuel starts to ignite late in the compression stroke, part of the combustion happens almost at constant volume. Before the piston reaches TDC, fuel starts to come in, and for a short period of time it ignites while the piston is almost still. What this means is that the heat addition process is split into two stages. One that can be assumed to happen at constant volume, and one at constant pressure once the piston does start moving considerably. A PV diagram would look just like either an Otto cycle or a diesel cycle between 4, 1, and 2, which haven't changed at all, with the difference here being a heat addition process at constant volume, similar to the Otto cycle between 2 and X, and a heat addition process at constant pressure similar to the diesel cycle between x and 3. The implications of these changes should be apparent if your Otto and diesel cycle bases are strong. The specific volume at 2 and x are the same, just like the pressure at x and 3 are the same. The heat in from 2 to x can be calculated as the change in internal energy, and the heat in from x to 3 can be calculated as the change in enthalpy. The total heat in would be the sum of these two. In the case where we use constant specific heats, we would write Cv times Tx minus T2 for the isochoric heat in, and Cp times T3 minus Tx for the isobaric heat in. Besides the compression ratio and the cutoff ratio explained during the diesel cycle's 10-minute lecture, we typically need to know the pressure ratio as well. This pressure ratio is that between the pressure at 2 and x. A TS diagram doesn't add much information to what we need for a dual cycle, but we can definitely draw one with isochoric heat addition between 2 and x, and an isobaric heat addition between x and 3. Let's look at a quick example where we use what we learned here, and if you want to check out other examples on this topic, make sure to check out the links in the description below. A dual combustion cycle has a compression ratio of 15 and a cutoff ratio of 1.2. The pressure ratio during the constant volume heat addition process is 1.6. Using constant specific heats at 300 Kelvin, determine the thermal efficiency when air enters at 90 kPa and 290 Kelvin at the beginning of the compression. As usual, try pausing here for a minute and solve this yourself before watching the solution up next. The thermal efficiency definition has not changed with respect to other gas cycles. Therefore, we need the heat out and the heat in. Let's begin with the heat out. The heat out still happens at constant volume like in Otto or diesel cycles. And since we're using constant specific heats, this is C sub V times the temperature difference. Since we have an isentropic process between 3 and 4, and we're using constant specific heats, we are going to need the volume ratio V3 over V4. V3 can be found using the cutoff ratio and the volume at x. We don't have the volume at x, but we know it's the same as the volume at 2. And V2 is V1 over the compression ratio. V4 is just V1, and since we have P1 and T1, V1 can be found with the ideal gas equation. Now for T3, we can use ideal gas between x and 3. We already have the volumes, but we need the temperature at x. And again, with ideal gas, we can find Tx in terms of T2 and the pressures. Since P3 is Px, this fraction is the pressure ratio. And finally, between 1 and 2, we have an isentropic process too, so T2 can be written in terms of T1 and the V ratio. We look up K and Cv for air at 300 Kelvin, like the problem asked, and we substitute all of the numbers that we can calculate to find the total heat out Q out. And now for Qn. We already saw that this is the heat coming in between 2 and x, plus the heat coming in between x and 3. One of them is isochoric, meaning that we use Cv, and the other one is isobaric, meaning we use Cp. We look up the Cp value for air at 300 Kelvin, and we substitute all the now known values to find Qn. And with that, we substitute the heats to find the efficiency. If you want to check out other diesel cycle or dual cycle examples, make sure to check out the links in the description below. You'll find the links to the other lectures of the thermo course as well as other engineering courses playlists. Thanks for watching.